if a wall power supply doesn't cut it, if we need things to be portable, if we need things to be useful in places where power is not accessible, then of course we turn to batteries. And we're super familiar with batteries. They come in big, huge sizes like we might find in our cars or our emergency power backups, or they might come in little tiny coin cells. We got the batteries that we put in our remote controls and use in all kinds of things, and we've got the batteries that power our modern rechargeable devices. Like laptops and drones and all kinds of stuff like that, right? Now, all of these batteries have slightly different sets of properties, and that's all related to their chemistry, how they work. And what a battery is actually what's called a chemical cell, an electrochemical cell. A single electrochemical cell is a really simple device. It's literally just a chemical reaction that's slowed down to the point where it's producing current. So the current, the electric charge that's being transferred is part of the chemical reaction that's happened. So usually what we have is we have two chemicals. One is an electron donor and one is an electron receiver. And one side we have an oxidation reaction that's happening that produces electrons, and the other side we have a reduction reaction that's accepting electrons. And as this as this chemical reaction occurs, electrons are flowing from one side of the battery to the other, and we use that flow of electrons to do work, right? Now, this is one simple cell, and the chemistry for all of these things changes drastically. We have some characteristics that this cell produces based on the reaction itself, based on what is happening, we get voltage. So a particular chemical makeup will have what's called nominal voltage, how much electrical potential energy there is between this side of the chemical reaction and that side of the chemical reaction. And that's how we get voltage for a particular type of battery. The capacity for the battery is related to how much charge can be transferred before the reaction is complete, before the chemical reaction no longer has any difference between the two sides, right? And if the electrons aren't flowing, if there's no electrons flowing, then there's no chemical reaction happening, right? So this is the size of the battery, how much of these two chemicals are available, how big the battery is, that's related to the capacity of the battery. And what a battery is really a whole bunch of these little cells. A little one-cell battery, like you might find, what this is that same sort of illustration, two layers of that chemical separated by a separator and then rolled up into a little round. So that's one cell most of the time in a battery. Big batteries or other sized batteries are just conglomerates of those cells. They might be lined up in parallel for higher capacity at the same voltage, or they might be lined up in series for higher voltage for the same capacity, or for some combination of the two to get bigger and bigger battery packs and to have those different characteristics that we need in our designs. There's a bunch of different types of chemistries of batteries. We're most familiar probably with the alkaline variety. These are the little batteries that we put in our remote controls and things like that. These are the ones you buy at the drugstore, stuff like that. Typically, they're not rechargeable. So an alkaline chemistry is not rechargeable. It's a one and done. You can't reverse the chemical process. These cells, each individual cell, has a nominal voltage of about 1.5 volts, and it comes in typical sizes of multiples of those, and that's going to be a theme throughout. So we most commonly see 1.5 volt cells, our one little AA's and stuff like that. But multiples of that, 9 volt batteries, 12 volt batteries, there are 6 volt lantern batteries, stuff like that. Those are all the alkaline chemistry, and they're just arrangements of those individual cells. We might also see lithium in hearing aid batteries or the emergency clock backup batteries and stuff like that. These you don't see very often. We don't deal with them very often in the modern world, but they're super awesome for little tiny projects and stuff like that. Their typical cell voltage is about 3 volts. They're not rechargeable, but you can get them in bigger sizes, double sizes, so you can get a 6 volt double stack of lithium battery. And these are one and done too. They're usually really expensive, but they're very high capacity for the size of a battery. So they have very high energy density, but not a they're not very cheap. Lead acid batteries are what you find in your car. So this is what your main car battery is. And each cell of a lead acid battery is 2 volts. These are not commonly used in embedded systems or our devices because they're so heavy. They're very, very dense. They have a high energy density, but they're also very heavy because part of the process, part of the metal that is used in these batteries is lead, which is one of the heaviest materials around. So we see these typically in stationary power backup rolls. They're very cheap to make, so they're very common in things that don't have to move or where it doesn't matter if you have an extra 20 pounds strapped to the thing. Most of our rechargeable batteries, the rechargeable AA's and stuff like that, are nickel metal hydride batteries. So these are another chemistry that is rechargeable. Their cell voltage is 1.2 volts, which is lower than the typical alkaline. So if you have a nickel metal hydride battery in your camera or something like that, and your camera doesn't know that it has a nickel metal hydride battery, it might start reporting a low battery before all of the charge is used up because it's seeing, if you've got 2 of them in there, it's seeing 2.4 volts instead of the 3 volts that would normally be in there. So these are a little screwy. We usually see these in arrays of like 9.6 or 12 volts for remote control car batteries and stuff like that. The new kids on the block are the lithium ion and LiPo batteries. These are what powers most of our rechargeable world, and these are very high energy density, lightweight, but expensive batteries, right? So these are very reusable, they're easy to charge, they're very, very common nowadays. And they have a high energy density that allows them to be pretty popular. They're still expensive, but because they're so high energy density and lightweight, they're used in lots of different devices. And because they're used in cell phones, they're getting cheaper and cheaper just because of the economy of scale of production. Their typical cell voltage is 3.7 volts. So we get a lot of weird arrays of batteries that end up with numbers like 11.1 and 14 volts. But those are the common numbers for lithium ion or lithium polymer batteries. So let's look at the label for these batteries. So say we've got one of these lithium polymer battery. The first thing I want to look at is what's my voltage? What is the voltage of this battery? So this is 7.4. That means it's 2 cells that are arranged in parallel, and at least 2 cells that are arranged in parallel and that are arranged in series, excuse me. That give me the 7.4 voltage. The capacity is the big number here, right? And what this capacity means is this is how much charge is stored in the battery, and that's represented in milliamp hours. So an amp is a coulomb per second, and a amp hour is a coulomb per second per hour. Right, so basically over an hour. So basically it's 1 amp delivered for 1 hour. 6,000 milliamps for milliamp hours is 6 amp hours. So this thing, if I was drawing a single amp from this battery, I could do that for 6 hours. Right? Or if I was drawing 6 amps from this battery, I could do that for exactly 1 hour. Right? Then there's this little 60C down here, and that doesn't have a really great representation. It's not, C is not a unit of electricity. What that is it's the discharge rate of the battery. Lithium-ion batteries, and actually all rechargeable batteries, have a safe discharge rate of some limitation, right? And basically, if the electrical reaction goes too fast, if we're drawing more than this discharge rate, the electrochemical reaction that's happening inside the battery goes too fast, the battery heats up, and it can cause internal damage. It can start to expand and things like that. And that's a big danger for these lithium polymer batteries, as we know from the hoverboard debacles, is they can explode if they're not handled properly. So that discharge rate is really important. And what that 60C means is that it's 60 times the capacity. So if I have 6 milliamp hours, 60 times that is what my safe discharge rate is. So let's look at ideal battery discharge. So here I've got my 6,000 milliamp battery, which is a 6 amp hour battery. I have a 60C discharge rate, which is basically I can take that discharge rate. My capacity is 6 amp hours. So 60 times C, 60 times my capacity, is 360 amps. So I can pull safely from this battery 360 amps. Now that sounds ridiculously high, but it's true. It's a very high discharge battery. They've worked out the chemistry. It's probably a lot of little tiny cells that have a lot of surface area so that the reaction can occur safely across all of them, with each one contributing just a little bit, and overall it comes up to a much higher discharge rate. So how long can I discharge at 360 amps? So my total amp hour is 6 amps, right? So 6 amp hours. So I could deliver 6 amps for 1 hour. If I'm delivering 360 amps, I divide my 6 amps by 360, which is 1/60 hours, which is 1 minute. So I can deliver 360 amps for 1 minute, right? That's enough. 360 amps is enough to weld. I could weld steel. I could weld steel with this battery for exactly 1 minute, which is crazy. I mean, that seems like a lot of energy, but it's still wild. So this is actually a really good battery, and this is very illustrative of how we can deal with the runtime of these things. Now, that 60C, that 6,000 milliamps, isn't real, right? So that's the ideal discharge rate. That's how much is theoretically in this battery. But what our real discharge is it looks something like this. As the voltage, as we put a load on our battery, the voltage decreases until it drops off precipitously. And if we go around this curve, if we start dropping too far past this little elbow here, then we run the risk of damaging the battery. Lithium polymer batteries in particular, if they are discharged too low, we're not able to recharge them safely. So we should never go past this little thing. And basically, if we want to calculate the real value of our capacity or anything like that, or real discharge time, there's a couple of things you should look up. I'm not going to go into them. It's Puchert's law or the Ragone plot, depending on what your battery chemistry is. If you're looking at lead acid or alkaline battery chemistries, Puchert's law works great. Ragone plots are usually included in the data sheets of lithium ion cells, so you can see exactly what your battery capacity is. But a great rule of thumb is just to assume that the discharge, the total capacity, is 95% of your rated capacity. We only get about 95% of what is actually there out of a given battery. And it changes over time as the battery ages too, which is really troubling. But for our designs, for the things we're doing, assume 95% of that if you're calculating runtime of some application.